So hello everyone. Let's see how to use this matrix.h library, which matrix.h library, which I built for the Brain OS project. Uh, so first of all, it's up on my Git repo. So you just have to like go there and like follow the instructions which are mentioned here, or else you just need to take the file which I will be emailing you and working on it. So after cloning the repo, as you can see on the right here, I have cloned the repo, and here is the file. Here is the folder. It's called matrix underscore ws, which is precisely the same thing. You can use any name of your choice. And now I am inside, as you can see over here, I am inside this. I'm inside this directory. So now, as the procedure here suggests, we first need to configure the library. So let's go ahead and do that. Uh, so we set the flag and we press enter. So you see this config.file object file gets generated here. And now let's just start this. And in order to save time, we need to give it the number of epochs for which we want to average out the execution time. So in order to save time, let's just give, let's say just 3 epochs and wait. So you can see it has started generating the configure.txt folder or file already. And it's currently testing the library with leaf size 8, that is an 8x8 matrix. If we go down, if somehow we go below 8x8 matrix, we switch on to the O(n) cube solution and start multiplying in the linear fashion. So I'll let this run for a moment. And before that, and in the meantime, let me just explain this example.cpp file, which is precisely this file over here. So yeah, it's already open here. So in this, there are, as we all know, there are two parts of this big library. One is for small matrices and the other is for large matrices. Uh, for small matrices, those can be defined like this, like matrix. Then we give the data type, then we give 2 cross the size of the matrix, and eventually we initialize the matrices. So let's say here we initialize matrix A, and here we initialize matrix B, and then we can. So these output stdio output operators are basically overloaded, which allows us to print the matrix. And so it's basically will print A, will print B, and then A into B, which is basically, here I'm using just the O(n) cube solution. And yeah, after that, it's all about, and now we can also write the A transpose of it. We can get the print the A transpose of it. Now we have the mat obj, which is basically, now we have the second class. So this is the class for big matrices. So we have the second matrix here, the second type of class here, which handles like large matrices, and we give this matrix, this class is given matrix in a CSV file format. So first we define the object for this matrix, and let's say that object is of type float. Now it will treat all these CSV, all the numbers, all the elements of, all the matrices of CSV files like A, B, and the answer as well as of type float. So we have to give the path to matrix A, then matrix B, then matrix C, and then just call matobj.matmul. Like that, we can like simply multiply the matrix. Now we have the other one, which is matrix transpose. This is basically it transposes matrix A, and then it stores in A underscore trans another new matrix. And as you can see above here, in over here, firstly it was checking with my leaf size 8. Now it has started checking the library with leaf size 16. And so basically, for the leaf size 8, mm, it had basically multiplied matmul. It had done this process 3 times and found the average over all the three. So 8, 16, and it will keep on going unless we get a minima, the minimum time. So let's get back to the example here again. Uh, Now we have another function which is again basically overloaded function of transpose, and then for that we have mat obg dot transpose, and we just simply give the matrix, the give the location of the matrix. So it basically, this is basically it does a in place matrix transpose. So it basically takes the output from a, takes the input from csv dot a, and stores the transpose of it again into csv dot a dot csv. And then this is a really common function which is basically, which basically just prints any matrix whose path is given by this argument here. And that's it. And yeah, and before this you just have to start, because you just have to include the namespace here, because the matrix.h has a matops namespace. Its namespace is matops, which is a abbreviated version of matrix operations. So now we can just wait a minute so that this gets finished. For that, for the time being, I'll just pause here. I'll pause the recording. So you can see it's actually checking for 120. It has reached till leaf size of 128, and it's still checking about. It's still checking the time taken for for the multiplication. Uh, just a note here: this configuration, which is currently going on, this is just meant for, just meant in order to optimize the matmul function. It's just because the matmul function uses the Stressen's algorithm, which is basically where I have written it in a recursive approach. So the thing is, the higher the, as it's actually written over here in my README file, which is like a very high value of leaf size leads to lesser recursion calls, but ends up giving more weightage to O n cube solution, and thus we have high execution time. And also on the other hand, a very low leaf size will lead to high number of recursion calls, but lesser weightage to O n cube solution. And this high number of recursion calls can again start building up, I mean, again building up, giving us high execution time. So we need to like experimentally find out the actual leaf size for which we get an optimal solution. So for my computer, as I had already shown this graph earlier, I had about, I mean, I had 26 seconds, 25 seconds, 24, 23 point something. And at approximately at 64, I had a sweet spot, which was the least of all, which I think I'll be getting again here because it's checking for 128 now. Let's see. So I'll pause for a minute. Okay, so as you can see, it has finished the configuration, and it has generated the configure.txt file. And this actually implies that it had checked the library with leaf size 128, but as it turned out, the average time taken to perform the multiplication of a 2000 cross 2000 matrix, which is actually stored here in this large matrix A and large matrix B, was higher when the leaf size was 128 as compared to 64, and 60, the time taken with a leaf size of 64 is much lesser than 8, 16, and 32. So as we can see, so we'll see the configure.txt file, you'll see the number is 64. That 64 number got stored here. That is the optimal value of the leaf size. So now we can go ahead and start multiplying and test and see how the whole thing works. So for the time being, let's just test the small matrix part. So what I'm going to do here is I'm going to define two matrices of data type double of 2 cross 2 and 2 cross 4, and like let's just initialize them as like 1 2 3 4 and 1 2 4 5, and like A is this, B is this now, and then I'm going to print A, print B, print A into B, which is the multiplication of A and B, and I'm going to print the transpose of A as well. So just for a better understanding, I can just put something like this here. Okay, now let's just compile this example, which is like g++ example.cpp.o. Let's name the object file as example as well. And there you go. You can see example file got generated. And now let's just run it. So there you go. You see A is 1 2 3 4, which is this, which actually matches with this. B is 1 2 4 5 4 6 7 8, which is this, and then the multiplication of A and B, which I'm pretty sure is correct. So let's just check it by numpy in Python. So let's define A, which is basically just a number here. So 1 2 3 4. Oh, sorry. Oh. So this is A, and this is B. So yeah, let's go 1 2 4 5, and then we have 4 6 7 8, 4 6 7 1 2 4 5 4 6 7 8. Right now let's just multiply into B. Oh. Yeah, so you see this matches with this answer, which is 9 14 18 21 19 30 47 47, and here also we got the same thing. And we can also see that we had printed a transpose. We had printed the transpose of A. So let's see what is A. A is 1 2 3 4, and the transpose should be 1 4 3 2. So here it is. It got printed here. I mean, I didn't write the print command for A transpose over here. That's why this didn't get printed. So as you can see, for smaller matrices, the matrix command works fine. Okay, now let's work with the bigger matrix object. Let's call two matrices here. Let's name this. Let's call one matrix, which is a.csv, b.csv, and then let's save the answer in answer.csv. So now let's like generate. First, let's generate. So I'll be generating two CSV files in this folder right here. One will be called a.csv and b.csv. So let's just check the path of my directory, which is home Shidaditya my matrix ws. So let's generate matrix A, which is basically all of ones. So we have 50 cross 50 matrix of ones, which is whose dimension is 50 cross 50, and that means, and let's just store A in a.csv. So you see it got generated here. And let's again generate a copy of A, but now just name it as b.csv. So there are like 50 ones on this, and there will be similarly 51s in this line as well. Okay, so now let's just generate another file, another same file, which is b.csv. Now b.csv is also 1, a.csv is also filled with ones. So the multiplication of a into b should be like all 50s, a matrix of all 50s. So let's just run this and see. Okay. What we can do is, after multiplying, we can also like print the matrix. But since it's going to be a large matrix, I'm not going to print it here. I'll just show it on LibreOffice. So let's just recompile example. Yeah, there you go. And let's just call this. Okay, now you see answer.csv got generated. And let's just open this up. There you go. Well, as you can see, we have all 50s here, all 50s here. But I know this is not a exact proof, so let's just prove it by using Python. So let's first of all let's just load it. Let's see from my library. Let's name it np.load. Wait a minute. Okay, so I had forgotten the syntax to get CSV into Python. So yeah, now here it is. So I have taken this file, which is answer.csv, and I gave the absolute path, and so it's here now. So this is the a.a from CSV file. So now let's just generate a 50 cross 50 numpy matrix, a random numpy matrix. So let's call it generated mat, which is np.ones 50 cross 50, and let's just run it. Okay, now let's just compare both of them. So there you go, equal to gen mat, and let's do for all. Oh, wait a minute. Okay, so it's list. Yeah, it's false now because it's all ones, but this was all 50. So I need a 50 cross 50 matrix of all 50s over here. Let's call it, yeah. So now it comes out to be true. Or else we could have also done it this way. So this is A, this is B. Let's do matmul A into B. Let's store it in answer from numpy. All right, now we can just compare answer from numpy equal to answer from my library for all. Yeah, see, it comes out to be true. So yeah, this is working. Now let's go and check out the. Okay, now let's just print this matrix altogether. So for that, I just have to uncomment this line and recompile. And let's just start example again. Oh, wait a minute. I didn't change this over here. So it will be answer.csv. Now we can, all right. Yeah, there you go. It also got printed on this matrix. And also we have another functionality inbuilt in matmul itself, which is we have a third variable here, if you just make that true, all these three matrices will be printed, which is kind of messy. So that's why I just put a flag there. So now if you see, you have the 50s here, you have ones here, this is the B matrix, and this is the A matrix. So you have all the ones printed here, and for B, all the ones printed here, and this is the answer, that is all 50s. So yeah, even this is working well. Now I can just comment this out. All right, now let's go and move on to transpose. Let's just generate, let's just mm, let's just build a new txt file here, name it new mat.csv. Let's just open that up and let's just put some values there. Let's say 1, 2, 3, 4, 5, 6, 5, 6, 7, 8. So now my aim is to find the transpose of this matrix and store it in a new matrix, which I'll be doing using this line right here. So let's give it the name, and that is new mat.csv. And let's give it another, let's store it in new mat transpose. Okay. Now let's compile and let's just run again. You see, we have this new matrix, new CSV file generated. So let's just open that up. Yeah. So you see, this was new mat, and this was new mats. This is new mats transpose. So it's 1, 2, 3, 4, 5, 6, 7, 8. So 5, 6 to 8. And now we have transposed it and stored it in 1, 2, 3, 4, 5, 6, 2, 8, 9. I chose a small example for this just for illustration purposes, but it will also work for other big matrices as well. Now we can do the similar stuff, but we can just, instead of storing it in a new matrix, we can do an in-place transpose, which is let's do it again here. There you go. So let's recompile and run again. So you see, previously you can see it has already started showing me reload because the file has itself changed. So it's the content of the file has changed. So it was initially, it was 1, 2, 3, 4, 5, 6, 2, 8. I mean, if we reload it, or if we like reopen it from here once again, it is 1, 5, 2, 6, 3, 2, 4, 8, which is again same as this guy. No, same as the initial transpose which we had. So yeah, there you go. This is after in-place transposition. And similarly, we can also print the new mat from this again, from this line again. So let's do new mat.csv, which is nothing but, so it will just print the new matrix. So let's go. Yes. So yeah, it had just printed 1, 5, 2, 6, 3, 4, 8. So yeah, that's it. And I hope this is the, I know there is a lot of scope for improvements since this was my first try for writing a library, but yeah, that's pretty much it. And it's there on my GitHub, which has all the detailed explanation of all the detailed explanation and where the code is and how is it working. And then there is also this doc.cgen documentation generated where you can go and see the example. And I mean, there is just one example, but then you can see the files I mean, let's see, you can see the classes which are there. So there are mainly two classes, which is one is for small size matrices and another is for large size matrices. So once you go inside this, you will get all the list of, so this is the main Stressen's multiply function, and then you have this matmul function as well, which actually calls this Stressen's multiply function from within. And and so you can just simply, I mean, go through each one of them and all the working. It's all written in a detailed format. You have, this one is for, yeah, this is all for the big matrix. So yeah, this is the Stressen multiply function. You can see there are like too many free statements here because there were like too many callocs I had done. But yeah, this is it. And yeah, also there is one more thing which I would like to just mention. So I did a, so this file also contains, I mean, it throws an exception when the matrix dimensions don't match. So for example, uh, let's say instead of 50 cross 50, I A is 50 cross 50 and I store it in a.csv, but B is, let's say, 51 cross 50 and we store it in b.csv. All right, now you see A and B got altered here. Now if we start multiplying a.csv and b.csv and try to store it in answer, the library will throw an error. So let's just compile it once. There you go. Matrix inner dimensions don't match. So yeah, matrix. Wait a minute. Yeah, so this was A into B. So once we try to multiply A and B, since A is 50 cross 50 and B is 51 cross 50, it doesn't multiply. But then if we just flip them, we do B and A, then you see it will not throw any error and it will simply give me the answer. So it's written in this big file here. Yeah. Likewise, similar thing was done for the small matrices as well. So for example, you define this matrix 2 cross 2, but what you do is you end up, let's say, storing, like by mistake you store another big matrix here, another row of numbers. So actually in reality this matrix size is 3 cross 1, not 3 cross 2, not 2 cross 2. This will again generate and throw an exception error. So there you go, wrong matrix dimension initialized. So the initialization is wrong right here. And then you have, and likewise you also have this. So now let's make I mean, there is also a mismatch in this matrix. I mean, if the inner dimensions don't match. So let's so for in this example, A and B inner dimensions do match and it won't throw any error. But let's say we make this 4 and this is 2. So 1 2 1 1 something here and 5 and let's say some 6. So it's 2 cross 4. Now if we this was 2 cross 4 and this is also like A is also 2 cross 4, B is also 2 cross 4. And now if we like just try to compile or like multiply both the matrices, it'll throw an error. There you go. I mean, it could print matrix A, it could print matrix B, but when it tried to do matrix A into B, there was a dimension mismatch and it threw an error. So yeah, that is pretty much it. And other than that, like I said before, yeah, there is a detailed documentation everywhere on the net, on my on the GitHub profile, and you can just go through, have a look, and please contact me if you guys have mm, any questions or anything. And you also have the terminal commands as to how to run the example file. Just the key is you need to keep the matrices. Actually, in this case, I kept both these matrices in this local directory itself, working directory itself. But you can keep these anywhere you want. You just need to give the proper path of b.csv, a.csv, the proper path, and it will just store it wherever you want throughout your computer. So yeah, that's it. Thank you.